Okay, in this video, we are going to talk about approximating areas under curves using Riemann sums. So we've been working with the derivative of a function, and we know that this gives us the instantaneous rate of change, and graphically it corresponds to the slopes of the tangent lines at the various points. So the antiderivative reverses the derivative operation, we know, but what does it mean graphically? What is the geometric meaning of that? So let's take an example. We know the velocity function of a moving object uh, for this example. And what can we learn about its position function? So let's say we have a car traveling at a constant velocity of 60 miles per hour along a straight highway over a 2-hour period. So if we have here the velocity on the y-axis and the time, right? So this will be our velocity and this will be our time. And we know that it's going 60 miles an hour, let's say for 2 hours between, say, 1 and 3. Then we have some graph that looks like this. And we want to know how far the car has traveled and what does this represent on the graph? Well, to get the displacement, basically, we would do the velocity times the time. Right? And so in this case, we would have the 60 miles per hour times the 2 hours, and that would give us 120 miles. Well, on the graph, that's exactly the area here, right? We multiply the height, this is a rectangle, we multiply the height of the rectangle, which is 60, times the base of the rectangle, which is 2, and we would get 120 miles per hour. So that's an interpretation. So objects don't necessarily move at a constant velocity, though. So what we can do when we have a non-constant velocity is we can divide the time interval into subintervals and approximate the velocity on each subinterval. So what that means is that we'll basically divide the time interval into many different rectangles and find the area of all these rectangles and add them up and use that to approximate the displacement, the displacement of the car or whatever in this case. So let's take this example here. Suppose the velocity in meters per second of an object moving along a line is given by this function, right? So again, we have on the y-axis, we have the velocity, and on the x-axis, we have the time. In this case, the units on the y-axis are meters per second, and the units on the x-axis are seconds. So we have x squared plus 1 with x between 0 and 3, and we want to approximate the displacement of the object. So what we do is we use n subintervals. In this case, we'll use n equals 2 subintervals. So what we'll do is we'll split between 0 and 3. We'll divide that in half. And so then we'll draw a rectangle. So how do we draw these rectangles? What we'll do is we'll approximate with a constant equal to the value of the function at the left endpoint, or we could do the right endpoint. But if we do the left endpoint, then what we'll do on this subinterval between 0 and 1 and 1/2, we'll draw this little rectangle right here. And if we find the area of that rectangle, then that approximates the area under the curve. Obviously, it's an underestimate because we're not counting the area of this almost triangular region up here. And then for this next subinterval, if we use the left endpoint, then we draw the rectangle like this, and we approximate the area under the curve here with the area of this rectangle. Again, obviously, this is an underestimate because we're not counting the triangular region here. Okay, so if we increase the number of rectangles to 4, then we basically would do this. We could split it in 2, and then we'd split it in 2 again. And again, if we use the left endpoint for each subinterval to draw that rectangle, then we're going to get these 4 rectangles. And you could see that each rectangle is again going to be an underestimate of the area under the curve in that subinterval, because of these little triangular regions. But this will get us closer to the actual area under the curve than if we use 2 rectangles. And then again, if we use n equals 6, right, we can get even closer. So we'll draw these 6 rectangles here, basically, in this case, using these what we call regular partitions between 0 and 3, and we'll use the left endpoint for each one. Now we could use the right endpoint, or we could use the midpoint for all of these subintervals. But you can see what happens is that we get closer to the actual value. Again, using the left endpoint here, we will still get this underestimate, but it gets us closer to the true value by using more rectangles. Okay, so this leads us to this idea of the Riemann sum. So f is a function. It's defined on some closed interval between a and b, and we divide it into n subintervals of equal length, these regular partitions, if you will. We take the delta x, which is b minus a, divided by n. That's the base of each of the rectangle. And then we use this x star k is some point in that subinterval, and we'll plug that into the function to get the height. So we basically have the height of the rectangle in the first subinterval times the base of the rectangle. And we're using that x value, plugging it into the function to find the height. And then we can do this for each of the n subintervals, right? So basically, we call this sum, summing all these rectangles, the Riemann sum for the function on this interval, right? And we can use a left Riemann sum, meaning the little sample points, the x star k's, are the left endpoint of each interval, or we can use the right endpoint. So the examples in the pictures below here, this first example, we use the left endpoint. You see the left endpoint is the height of the rectangle for each subinterval. We can use the right endpoint, same graph, same f of x, but now each subinterval, instead of using the left point like up here for the height of the rectangle, we're using the right endpoint. And then we have the midpoint Riemann sum. Basically what we do is we plug in the midpoint into each function, into the function, and we get the height of the rectangle right there, right? That would be our f of x star k for the midpoint. Okay, let's do this. Let's use this for an example here. The rate at which water is being pumped into a tank is given by a continuous increasing function r of t. We have a table of selected values. So in this case, we don't have the explicit function, but we have a table of values for t between 0 and 13. We want to use the left Riemann sum with 4 subintervals. Well, notice we have 5 points here, so we're going to use 4 subintervals. So the first is going to be 0 to 4, and the second is going to be 4 to 6, and the third is going to be 6 to 10, and the fourth subinterval is going to be 10 to 13. Okay, that gives us 4 subintervals. We're going to use the left Riemann sum. So in this case, we'll do f of 0, which is equal to 7. So 7 is the height of the rectangle. That's given by the value of the function. And the base of the rectangle is 4, right? 4 minus 0. That's our x values. And then we'll add that. In this case, we'll use the f of 4. And f of 4 by the table is 13. And the base of the rectangle is 6 minus 4, which is 2. And then again, left endpoint, f of 6, looking at the table, that's going to be 18. And then the base is 10 minus 6, which is 4. And then for the last one, left endpoint, f of 10, which is 23. And we'll multiply that by the base, 13 minus 10, which is 3. So we get 28 plus 26 plus 72 plus 69 for a total of 195. This is going to be gallons, right? So between 0 and 13 minutes, 195 gallons total are pumped. into the tank. Okay, now the question is this approximation greater or less than the true value? Well, we can go ahead and graph this out. We'll plot R of t on the y-axis, that's gallons per minute, and time on the x-axis, 0, 4, 6, 10, 13. So I'll put a 13 right there. A little bit less than half of that is going to be 6. Somewhere right about somewhere in here is going to be 10. And then we have 4 and 0. And on the y-axis, we'll have at 0, it's equal to 7. So we'll go up to 27. We'll do half of 27. We'll put 13, a little less than half. 18, 23, and 7. So we have this point, this point, this point, this point, and this point here. Now it says this is it's a continuous and increasing function. So it might look something like this. And we're using the left Riemann sum. So we're using that rectangle for that first interval, this rectangle for that second interval, this rectangle for that third interval, and finally this rectangle for that fourth interval. And we can very clearly see then that this is actually an underestimate of the area under the curve because of these little almost triangular regions above each of the rectangles that we're not counting. So this is less than the true value. And that's it.